In this video here, we're going to take a look at the Taylor series. So just recall then when we first introduced the Maclaurin series all the way back in Core Pure. And the Maclaurin series allows us to write a function of x as an infinite series in ascending powers of x. However, the conditions of the Maclaurin series expansion sometimes means that we can expand certain functions such as ln x in this way. Now the Maclaurin series focuses on x equals 0. But for a value of x very close to 0, a few terms of the Maclaurin series may still potentially give a decent approximation of the function. But this breaks down as x moves further and further away from 0, even if it still falls within the interval of validity. So the way that we overcome this problem is by deriving a series expansion focusing on x equals a. And this series expansion is what is known as the Taylor series and is a more general form of the Maclaurin series. So to get us started here then with the Taylor series, let's just consider the functions f and g, where f of x plus a is identical to g of x. Then in that case, the half derivative of the function f at x plus a is equal to the half derivative of the function g at x. And in particular here then, the half derivative of the function f at a is equal to the half derivative of the function g at 0. So the Maclaurin series for g then, which you should be very much familiar with by now, right from Core Pure, becomes the following here. So this expansion here is what is known as the Taylor series expansion. And if we replace x by x minus a, then we obtain another useful form here. So as we've just mentioned, right, just replace x by x minus a, and we obtain this form here. And again, this form here is also known as the Taylor series expansion. So let's just quickly summarize then this introduction here to the Taylor series. So the Taylor series expansion can be given as, so for the first expansion here then, this is for f of x plus a, and we obtain this expansion here. We also have this alternative expansion here then for f of x, as you can see here. And the expansions given above are known as Taylor series expansions of f of x at or about the point x equals a. And the Taylor series expansion is valid only if the nth derivative of the function f at a exists and is finite for all n belonging to the set of natural numbers and for values of x for which the infinite series converges. And the final point here then is to note that neither expansion is given in the formula book, so it's just important that you do familiarize yourself with these two results. Often, an exam style question based on the Taylor series will give you the relevant result, but it isn't a given, so I would just recommend that you do learn these two results here. Okay, so that concludes this introduction here to the Taylor series. Let's just work through a couple of practice questions. So let's get started then with question 1 here. So for the first part of this question, part A, it just asks us to find the Taylor series expansion of root x in ascending powers of x minus 4 up to and including the term in x minus 4 cubed. And you might have already noticed it here, but we are actually given the relevant result then for the Taylor series expansion of f of x about x equals a. So that just makes our life a little bit easier here. And before we start with part A then, let's just note here that we're expanding about x equals 4. Okay, so for the first part of this question then, part A, we start with f of x here, which is equal to root x here. So that's our starting point here. So f of x is equal to root x, okay? And what we also require here is f prime of x. So f prime of x. We also require the second derivative. So f prime of x is the first derivative. We also require the second derivative. And then finally here, we do require the third derivative. Okay, and at each stage here, what I also need to do is evaluate each one of these at this point here. So x equals 4. Okay, so for example then, for the first one here, this will be f of 4. So nice and straightforward then, the square root of 4 here is 2. Okay, let's just keep going then. So f prime of x here, so all we need to do here is differentiate root x with respect to x here. And if you do this correctly then, should hopefully be nice and straightforward. But if you do this correctly, what you should get here is 1 all over 2 root x. Okay. Again, don't forget to evaluate this here at this point. So f prime of 4 is equal to, let's substitute x equals 4 into this expression here, and you should obtain 1 over 4. Let's just keep going. And now for the second derivative here, just differentiate this here with respect to x. So you should get then minus 1 all over. So we get 4x to the power of 3 over 2. Like so. Again, don't forget to evaluate this here. At this point here, if you do this correctly, what you should obtain here is minus 1 over 32. And then finally here, for the third derivative, just differentiate this here with respect to x. So if you do this correctly then, what you should obtain here is 3 all over ax to the power of 5 over 2. And then finally here, don't forget to evaluate this at this point here. So f prime 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 at 4 is equal to, so what we get here then is 3 over 256 there. Okay? So at this point here then, we now have everything that we need to find the relevant Taylor series expansion. So therefore, f of x here is equal to, so what we're going to do here then is use this result that we were given at the beginning of the question. So f of x equal to root x here, which is equal to, so we start with f of a here, that would be f of 4, which is 2. We then have f prime of a, so that's 1 over 4, and we times that by x minus a here. So a in our case is 4. So I get plus 1 over 4, so plus 1 over 4 times by x minus 4. Like so. We then have f prime prime, so that's the second derivative here. So that's minus 1 over 32. We divide that by 2 factorial, so just be careful here. So minus 1 over 32, we divide that by 2. So that gives us minus 1. So that should be a minus here. Let me just change that. I'm getting carried away, so let's just slow down a little bit. So minus 1 over 64. So minus 1 over 64. We then get x minus 4 squared, like so. And then finally here, we have the third derivative, so that's 3 over 256. We divide that by 3 factorial, so we divide that by 6, right? So 3 factorial is just 6. So in that case then, if we do this correctly here, what we get is plus, so plus 1 over 1536. And then we times this here by x minus 4 cubed. Okay. Obviously, this would just keep going on and on, but we're only concerned about going up to x minus 4 cubed. Okay. So there we have it. That gives us the solution to part A. Hopefully not too challenging, right? So now for part B then. So let's just box this off here. That was part A. So now for part B then, it says, hence, estimate the value of root 5 here. So if we want to estimate the value of root 5, what I need to do here is substitute x equals 5. So substitute x equals 5 into f of x here, right? Into this Taylor series expansion. So if we do that here, then what do we get? Well, as you can see here, the x minus 4s will all just simplify to give me 1, because 5 minus 4 is 1. 5 minus 4, again, is just 1. 5 minus 4, again, I just get 1, right? So what I'm going to get here for root 5 is approximately, I'm going to get 2, can't do anything with that, plus 1 over 4 times by 1. I get 2 plus 1 over 4. We then have, so at this point here, I've got minus 1 over 64 times by 1 squared. So 1 squared is just 1, right? So I've got minus 1 over 64 times by 1. I get minus 1 over 64. And then finally here, well again, this x minus 4 to the power of 3. If I substitute x equals 5 into that, I just get 1 cubed, which is 1. I get plus 1 all over 1536. So what we need to do here then is just basically use our calculator, right? Just put this right-hand side here into your calculator. And if you do this correctly, then what you should find here is we get 2.235 here. Okay. So let me just quickly grab my calculator here, because basically we can give So let me just quickly grab my calculator here, because basically what we can do is give our answer a quick sense check, right? So if I put root 5 into my calculator here, what do we get? So I get 2.236067977. Our estimation here was 2.235, so it's pretty close, pretty accurate, and it seems sensible. Obviously, if you get something completely different, for example, if I got, I don't know, 3.821, for example, just some random number that's completely off, then something's probably gone wrong somewhere. Either the expansion here would be incorrect, or I've substituted the wrong value into f of x, okay? But you can always kind of give your answer a quick sense check there, just to make sure it seems sensible, okay? So there we have it. That gives us the solution to part B and the solution to question 1. So let's have a go now at the very last question here, question 2. So for question 2, then it asks us to express cos of x plus pi over 4 as a series in ascending powers of x up to and including the term in x cubed. And as we can see here then, again, we are given the Taylor series expansion of f of x about x equals a, as we can see here, okay? So to begin with here, what I'm going to do is I'm going to let f of x, so we let f of x be equal to cos x, okay? So in that case then, if we want to express cos of x plus pi over 4 as a series, then in that case, cos of x plus pi over 4, so cos of x plus pi over 4 is equal to f of x plus pi over 4. Like so, okay? So what that means here then is that a is equal to pi over 4. So this Taylor series expansion here will be about x equals pi over 4. So what we need here then is f of x, which we're already given, right, or we've already expressed here. So f of x is equal to cos x. What we also need here then is f of x about this point here, okay? That would be f of pi over 4. So that is cos of pi over 4, which is simply root 2 over 2. We now need f prime of x here. So f prime of x here. So just differentiate this here then. Nice and straightforward. We simply get minus sine x. Okay. And again, what we need here is f prime at this point of pi over 4. So f prime pi over 4 here, which if we evaluate this gives us minus root 2 over 2. Okay. Now what I need to do here is keep going until I get to the third derivative, because we're going up to the term in x cubed here. Okay. So f prime of x here, that's the second derivative. So just differentiate minus sine x here with respect to x, and this gives us minus cos x. Get minus cos x there. Again, we need to evaluate this at the point pi over 4. F prime of pi over 4 is equal to, so that would be minus root 2 over 2. And then finally here, we need the third derivative. Okay, so for the third derivative here, just differentiate minus cos x, and this gives us sine x. Okay. And again, we need to evaluate this here at pi over 4. And if we do that here, then we simply get root 2 over 2. Okay. So at this point here, then, we now have everything that we need to find or express cos of x plus pi over 4 as a series in ascending powers of x up to and including the term in x cubed. So what I'm going to do here then is use, so we do that over here, I'm going to use here f of x plus a, so f of x plus a here is equal to, so this was for f of x here, right? Because we have cos of x plus pi over 4, I'm going to use this Taylor series expansion here, okay? So for this Taylor series expansion here, this is simply f of a, so f of a plus f prime of a times x, so f prime of a times x plus, we then have f prime of a all over 2 factorial times x squared. And then finally here, we will have f prime 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 of a all over 3 factorial times by x cubed. Okay. And of course, this just keeps going on and on. We're only concerned about going up to the term in x cubed. Okay. So using everything that we've got here then, in this case here, cos of x plus pi over 4 is equal to, so I have f of a here. So f of a is root 2 over 2. That's root 2 over 2. We then have f prime of a times x. That's going to be minus root 2 over 2 times x. So minus root 2 over 2 times x. We then have f prime prime of a over 2 factorial times x squared. So this is f prime prime of x here. So f prime prime of a, that's f prime prime of pi over 4, is minus root 2 over 2. If I divide that by 2 factorial, what I'm going to get here is minus root 2 over 4. Okay, so just be careful there. So minus root 2 over 4 x squared. And then finally here, so we have f prime 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 of a over 3 factorial times by x cubed. So this is f prime 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 of a, which is pi over 4. So that's root 2 over 2. We then divide that by 3 factorial. So 3 factorial is 3 times by 2 times by 1. That would be 6, right? So just be careful here then. What I get here is root 2 over 2. We divide that by 6, so I get root 2 over 12. Okay, so plus root 2. So plus root 2 over 12 there. Okay, and don't forget the x cubed, of course. Like so. Now what we can also do here, just to make the solution look a little bit nicer, is factor out the root 2 over 2. So therefore, cos of x plus pi over 4 is equal to, so as we've just mentioned, then factor out the root 2 over 2. So root 2 over 2 here. We've got our bracket then. We get 1 minus x here. We then get minus a half x squared. So minus a half x squared. And then finally plus 1 over 6 x cubed here. So 1 over 6 x cubed there. Okay. Of course, that would just keep going on and on. We're only concerned about going up to the term in x cubed. So that's absolutely fine there. And there we have it. So that gives us the solution here to the very last question, question 2. And that brings us to the end then of this video here on the Taylor series.